Good morning, students. Today's class we are going to study about the moving average filter. So here we are proposing a time domain technique to remove the random noise which is present in the signal, only one realization of the signal or event of interest. So here the ensemble of several realization is not available, but this ensemble means total of several realization is not available, or a synchronized averaging technique is not possible in this. So, and also temporal averaging for noise removal is not possible in synchronized averaging. So that's why we are going for moving averaging technique. So in this moving averaging techniques, the concept is we have a window. So that window will be placed over the signal, and the window will function. So the window characteristic will be multiplied over the signal. So whatever the signals which lies within that window will be extracted. Whatever the signal which falls outside that window will be removed, clipped off. So from that we will be moving the window from each and every part of the signal, so that to clip the noise and then to extract the signal alone. So that is the concept of this moving average window. So here the moving average window comes under the FIR filter. So here when you see the general form of an MA filter, moving average filter, it is like an FIR filter characteristics. So which is given by the formula y of n equal to summation k equal to 0 to n bk x of n minus k, where x and y is represents the input and output of the filter, bk represents the filter coefficients or tap weights, and n is the order of the filter. So when you see this is a structure, transversal structure of a filter, so in which x of n with a delay and it is multiplied with b coefficients, and finally it is averaged here to obtain y of n. So this equation is represented in here in transversal structure. So the transfer function h of z is given by b0 plus b1 z inverse plus b2 z power minus 2 plus etc. bn z power minus n. So when the moving average filter to remove the noise, the filter we call it as a Hanning filter. So the characteristics is defined here as y of n equal to 1 by 4 x of n plus 2 into x of n minus 1 plus x of n minus 2. Now let us assume the x of n equal to del of n, it impulse function. Then this x of n, it is replaced by wherever you have x, it is replaced by del. Then after that, when you apply this transform for it, you will be getting the transfer function h of z as 1 by 4 of 1 plus z inverse the whole square. Then this is the signal flow graph of a Hanning window for this particular response, 1 by 4 of 1 plus z inverse whole square. So this is the transfer function of a Hanning window. So the MA filter, it is a finite impulse response filter, and it is having finite number of terms, and it is realized non-recursively with no feedback. So the output depends only on the present input sample and few past input samples. And if you see, the filter is a set of tap weights of delay stages, and this FAR filter is a linear phase characteristics. The weight is symmetric or antisymmetric in nature. So it is inherently stable. And when you see the frequency response, you can substitute z equal to e power j omega t in the h of z. Then we will be assuming certain terminologies called t is the sampling interval, f is the frequency in hertz, omega is the radian frequency, and t equal to 1, which is assumed set it here, and the frequency varies between 0 to 1. The frequency response of a Hanning filter is given by h of omega equal to 1 by 4 of 1 plus 2 e power minus j omega plus e power minus j2 omega. That means in the place of z inverse, we replace with e power j omega here. And e power minus j omega equal to, when you expand, it is cos omega minus j sin omega. So when you substitute in this formula and then when you simplify, you will be getting the expression as h of omega equal to 1 by 4 of 2 plus 2 cos omega into e power minus j omega. Then the magnitude and phase response is given by modulus of h of omega equal to modulus of 1 by 2 of 1 plus cos omega. For phase response angle, it is minus omega. And this is the magnitude and phase response of a Hanning filter, which is called as a smoothing filter. So this is the magnitude response and this is the phase response. Phase response is like a linearly decreasing one. And for more smoothing, we can increase the filter delay. So y of n equal to 1 by 8 summation k equal to 0 to 7 x of n minus k. So when you expand, after that when you apply the Z transform, you will be getting the expression as 1 by 8 of 1 plus exponential minus j4 omega into this term. And then we will be finding out the zeros. and attenuations after 100 Hz is non-uniform, phase is not linear and piecewise linear. So the magnitude and phase response of an 8-point moving average filter, it is like magnitude will be getting like this, and in the phase response you can get this like this. Thank you.